How's it going, everybody? Welcome to this next lecture. And today's we're gonna dive into Kubernetes, into container orchestration, and get into the real meat of what we're gonna be talking about the rest of this course. There's gonna be quite a bit of material, and I fully recognize that some of it may go a little over your head, especially this first time around. But hang in with me, and as you get more exposure, more experience over time. And as you do the hands-on, hopefully it'll help sink in a little bit of what we're talking about. So with that in mind, let's go ahead and jump into the slides, and we'll go from there. So for today, the goals and the outline are as follows. We're going to start off with a little bit of an introduction to container orchestration, because Kubernetes isn't the only orchestration framework that's out there. Then we're going to talk a little bit about the Kubernetes architecture, still at a pretty high level. We're not going to get down into the weeds of things, but just at a high level. Then we'll talk about pods and what they are. We'll talk about using YAML to define our desired state. And then finally, just a little quick snippet on accessing your pods using port forwarding. Now, I know that, again, that sounds like a lot. We'll make it through, okay? So if you remember last time, we talked a little bit about containers and how they've really changed the game because they've let us more or less standardize the way that we define applications. We can package them up and we can ship them around. So a machine that doesn't have the various components installed, well, the container image provides that. That process runs in isolation, and then I can run an application on the machine that it might not have been able to before. Okay, and this standardization brings benefits. Okay, so just like in the normal shipping world, when the shipping world decided to standardize around a box, it provided a lot of benefits. Okay. The shipping industry can then standardize and focus around, all right, we know the box is a certain size, that certain height, I can stack them so high, they've got locking mechanisms on the corner so I can anchor them to ships, etc. And they could start building cranes and freights and truck chassis and whatnot that know the size of the box, and they don't have to care about what's inside of it anymore, okay? They can use software to track the movements and automatically track, okay, it came off the ship and went onto this truck and moved into this part of the yard, whatever, okay? And this standardization, again, is what really allowed the shipping industry to really take off compared to what it was in the past, okay? Now, much of that is happening today with software containers, okay? So again, remember, all a machine needs to do in order to run a container is have a container engine, okay? Now, so the question is, what if we could start building some of these higher level abstractions? Imagine that, kind of like an air traffic controller, imagine that if I had a fleet of machines and if I ran a small little agent on each machine, what if I had the ability to communicate with that agent and say, hey, here's some instructions, start up a container on your machine. And now machine number 3 over here, start this container on that machine. And you can start to orchestrate, hence the name orchestration. You can orchestrate kind of like the conductor and choose who's doing what part, okay? Now, of course, there's more to it than just running containers. We've got to worry about networking and storage and a lot of other things. And for today, I'm going to skip all that. We'll talk about that again in the future. But if I could start to kind of group these machines together and use these little agents, what additional power does that give us? And really, at the end of the day, that's exactly how container orchestration works, okay? So container orchestration provides the ability to manage potentially a fleet of machines. You can also run it all on a single machine. Like, for example, I can run Kubernetes on just a single Raspberry Pi. And so then I can use that to manage the containers that are running on that. But the second and third bullet points here are really the fundamental of container orchestration. Okay? So as an administrator or as an application admin, whatever, I can define expected state. And by that, what I mean is I can say, this is what I want to happen. I want this image, I want these ports, these volumes, I want 3 instances of it running. I want it to update so that it rolls out one at a time, etc. And I can define a lot of these policies. And again, I'm not telling it how to do it. I'm just saying, this is what I expect. Now make it so. And then the orchestration framework works really hard to try to make the actual state reflect your desired state, your expected state. Okay. So for example, if I said I want 3 instances of this application running and one of them goes away, well, then it will say, well, hey, you wanted 3, there's only 2 running here. Let me spin up a third one and get it back up. Okay. So it'll do its best to reconcile. And that's really how the whole system works. It's really event driven in the sense that when an event happens, it looks to see how does that affect our actual state, and does actual state reflect the desired state? And if not, how do we reconcile? How do we get back to it? Okay. So again, you're going to hear that a lot of this desired state, expected state idea. Now, in container orchestration, there's typically 2 types of actors when it comes to machines. Okay. And these 2 different types of actors can have different names depending on which orchestration framework, whether you're using Kubernetes or Swarm or Nomad or ECS. But at the end of the day, this is kind of how it works. Okay, I'm going to grab my laser pointer here. Boop. All right. So there's the managers or masters, and they more or less serve as the brains of the operation. These are the nodes, or it's the agents that you give the desired state to. And you say, hey, brains of the operation, I want 3 of these containers running. And they say, cool. Now, where do we schedule it? How do we make it work? Then on the flip side are the workers or the agents or the nodes, just depending on which framework you're using. And they're the ones that actually do the work. Now, a lot of times in clustered environments, the manager nodes are separate from the worker nodes. They're completely different machines. So then the manager nodes can really focus on managing, and then the worker nodes can work. But it is possible that they're one and the same. For example, going back to my Raspberry Pi example, I can have a single Pi that's running Kubernetes, but in that case, it's both a manager and a worker. So they're not always separate, but in large clustered environments, they pretty much always are. And a lot of the managed Kubernetes services like EKS with AWS or GKE with Google, they run the managers. And so somewhere in their infrastructure, they have the managers running, and then you run the workers and add capacity to your cluster. Okay. Now, so let's talk about Kubernetes a little bit. Okay. So Kubernetes is a container orchestration framework that was originally actually developed and contributed by Google. And it was contributed to a group called the CNCF, which is the Cloud Native Computing Foundation. And the CNCF is a foundation that has lots of open source projects. Kubernetes just being one of them. And Google, for the most part, when Docker brought containers and just made it really easy, Google said, hey, welcome to the container world. We've been doing this 10 years internally or however long. Here's the best of what we've learned, and basically contributed this framework so that the rest of the industry could come on. And it was based on a lot of their internal stuff. One of the systems is called Borg, yes, from Star Trek, but it's not the exact same structure, same setup and everything. So again, Kubernetes can be used to manage clusters of one node or thousands or even tens of thousands of nodes. It can get quite large. In case you're wondering what Kubernetes actually means, Kubernetes kind of plays along the nautical theme that a lot of the Docker and the containers and this whole ecosystem uses. And so it's actually Greek for helmsman or pilot. And a lot of times you see it abbreviated to K8s, K8s, and there's basically the K and the S are the first and last letter, and then there's 8 letters in between. So that's how you get K8s. And so you'll see me reference it that way or write it in my slides quite a bit that way too. In Kubernetes, again, just as any other orchestration framework, it works by declaring desired state. And there's a couple of different ways to do that, but the preferred way is to use what are called manifest files. And these are files that are written in YAML. If you need help with YAML, check out the other video that dives into the YAML. And these manifest files declare the desired state. Once submitted, Kubernetes just validates the structure of the YAML, makes sure that it's syntactically correct, and then it stores it. And from there are components, controllers, that observe that change of, hey, this new state was declared, and they say, all right, hey, I'm in charge of the pods. I saw this new pod definition show up. Let me go make it happen and go from there. And the really cool thing about Kubernetes is this last bullet point, custom resource definitions. And again, we'll talk more about CRDs later on. But at a high level, what they do is allow you to extend Kubernetes and define your own objects. So, for example, one component, one system that we use here at Virginia Tech is called Cert Manager. And Cert Manager defines CRD so that I can declare and say, I want a certificate, which isn't an object that's natively in Kubernetes, but I can declare a certificate and it will go and provision a TLS certificate and allow me to use that to secure my, my HTTP endpoints. So pretty cool stuff. So at the end of the day, it's important to remember that Kubernetes is really a system that allows you to declare desired state, and then controllers can respond to that state or changes in the state to perform actions. Okay. Yes, the native and the default objects were very container based, but it extends much more beyond that. Okay. Again, the Kubernetes architecture, we've got master nodes and they're the brains of the operation. And what's really important to note is that everything that happens with Kubernetes comes through an API server. And so it's just an HTTP endpoint, and there's an API that you can say, hey, get the list of running pods or config maps or secrets or whatever. And all that's happening through the API server. Even all the other components that are running down actually on worker nodes, the kubelet, and I'll explain what these are in just a minute. All of these interact with Kubernetes through that API server. Nothing talks directly to the database except for things that are kind of part of the API server, which is really cool. Kubernetes, by default anyways, uses a system called etcd as its database. And what that allows it to do is if I'm running Kubernetes in a highly available mode, I have more than one master. I might have 3 masters, or if I've got a really large cluster, I may run even 5 masters. And, anytime that I make changes to one of them, I want all of them to be able to see the changes. And etcd is a database that supports the clustering and a lot of the other really complicated things of making sure that everybody's got the same copy of the data. And again, we're not going to dive down into quorums and leader election and how they make sure that they don't partition each other off from each other. There's a lot of really complicated distributed computing algorithms and things that go into that. But the cool thing is it takes care of all that for you, right? Again, controllers are what watch for the state change and then perform the various actions on the cluster. Okay. So again, I just define state, controllers make it happen. Okay. Now, if you remember earlier, I talked about, wouldn't it be nice to run a little agent on each machine and then kind of tell that agent what to do? More or less, that's what the kubelet is. The kubelet is a little agent that runs on every node in the cluster, and it's what coordinates all the state and what's happening on that node back to the masters. So if a container dies, well, the kubelet is the thing that tells the master node and says, hey, I had a container just die here, just to let you know, kind of thing. Kubeproxy, we'll talk a little bit about later, but it manages a lot of the networking rules so that if one container needs to talk to another container, but it's on another node, kubeproxy is what makes a lot of that magic and glue happen. And again, we'll talk about that a little bit later. And pods, all right? This is the first time I'm actually defining pod, and I know I've mentioned it several times, but a pod is the most basic schedulable unit in Kubernetes, and it consists of the actual running containers. Now, so a pod can be one or more containers. We're going to start off with just single pod containers, but we'll talk about examples of when you want multi-container pods in the future. Okay. So for now, anyways, you can think of a pod as just a single container that's running, okay, and all the configuration that's needed for that. Again, we'll talk about more advanced use cases later. So let's dive a little bit more into pods. Again, a pod is the most basic schedulable unit in Kubernetes, and by scheduling, I mean Kubernetes gets a request to run a container, and okay, it's not a container, it's a pod, but it gets a request to run a pod, and so it schedules it, it assigns that to another node to actually run it, okay? And again, a pod can consist of one or more containers, but what's nice about this is that the pod, if a pod has more than one container in its definition, it's guaranteed that all those containers will be co-located. meaning that if a pod has 3 containers, they're guaranteed to all run on the same machine, on the same node. So you'll never have the case in which a pod may have 1 container on one node and then the other 2 containers on another node. They're guaranteed to be scheduled together. Okay, and there's various reasons for that. We won't get into all of it until we get into multi-container pods. Each pod also gets its own IP address, and kind of going back to the networking, that becomes very important. So you can communicate with a pod, with pods individually, even when they're running on the same machine. We'll talk more about networking starting a little bit next week. All right, now let's learn how to actually declare the state. Okay, so most interactions with the Kubernetes API use a tool called kubectl, kubecontrol. It just depends on who you're talking to, but there's a lot of debate on what's the actual name of this thing, okay, or how to say it correctly. So I'm going to mix it up quite a bit, but you're welcome to choose whatever pronunciation you want. At the end of the day, it's a CLI that interacts with the Kube API server. So it's making a API request, and then it formats the JSON data that it gets back into a command line interface to just make it easy to see and interact with. Okay? And there are 2 main ways to create the resources. We can either do it directly through the CLI or use the manifest files that I talked about earlier. We'll start off first through the command line, and then we'll transition to using the YAML or the JSON manifest. Okay. All right, so let's make our first pod here. We're going to run this command. And so this says kubectl run, which is the command. We're going to specify the image that we want to run, and then the name of the pod. Okay, and that's pretty much it. And then so this is declaring the state into Kubernetes to say I want to run this, and then it will say cool. Let me figure out how to make it happen. Once it's up and running, we can use kubectl get pods, and then that's going to make an API request to the API server and say, hey, what pods are running? And it will tell me, hey, you just ran this pod, and here's the results. The ready 1 out of 1 tells me that in this case, this pod only has 1 container, and so 1 out of 1 of it's running. It hasn't had any restarts, and how long has this container been running? Okay. If I want to get additional details about the pod, I can use the describe command. And so if I do kubectl describe, I'm going to describe a pod. When we talk about other types of resources in Kubernetes, we may swap pod with config map or secret or service, or there's lots of different things. So I'm going to describe a pod named hello world, and then it gives me a ton of output, and we'll see an example of some of that output here in just a minute. All right, and then maybe we'll just go straight to the demo right now. And so let's pull up the terminal here, and I'm gonna run that same command that we were just looking at. So image equals mixer87 hello world, and I'm gonna name this hello world. And once I do that, it's going to I didn't delete it from earlier, but here's how you delete. You can use the delete command. All right, so it tells me that the pod's been deleted. Now, when I run it, that's what I get for not cleaning everything up before when doing my run through. But I see that the pod's been created, and I can do a kubectl get pods, and I see that it's running, and now I can do a kubectl describe pod hello world. And let's see what output we get here. So there's a lot here. And again, I'm not going to explain all of this now, because a lot of this is going to make sense when we dive into like networking or debugging, that kind of stuff. But namespaces default, we'll talk about namespaces in just a little bit. The start time, what labels were applied to it. We'll talk about labels next week when we talk about services. The IP address that was given to this pod. And then I can see the container ID. So 335. So actually, if I do a Docker PS and grep for 3353, I will actually see a Docker container on my machine that's running. So Kubernetes, while using Docker desktop, actually uses the Docker engine to launch the containers. And so that's why there's the Docker prefix to the container ID there. There's the image that it used, the full image ID if you want to get the SHA-256 hash for the actual image that it used. When it started, what mount points, various conditions, volumes. The events here are going to be very useful when we talk about debugging containers. So if something doesn't start, I can look at the events to find out why it maybe didn't start. But in this case, everything started up nice and easy for me. So, and it pulled the image in less than a second. I already had it pulled, so it didn't actually have to pull down new layers. So in this case, I'm going to go ahead and just delete the pod to prepare for my next demo, and we will jump back over to the slides. All right, so let's talk about using YAML to define our state. YAML is it's debatable. There's a lot of people that are like, oh, I hate it and all this kind of stuff, but it's used all over the place, especially in the cloud native industry, I guess, to define configuration and to define state. So Kubernetes just kind of goes along with that. And the question comes up of why should we use manifest files rather than, okay, here's a bash script of stuff. And honestly, it's because managing files is much better, much safer than just a bunch of commands. And the big reason there is it's easier to share it with others. If I define an application, I can put it in a YAML document, and I can even just host it on the web, and people can pull it directly from the HTTP endpoint, or I can put it in a Git repository and version control it. There's just a lot more flexibility that comes along with using files instead of straight up commands. And I can also create and delete many objects either within a single file or a directory, and we'll see examples of that here in just a minute. When I declare Kubernetes objects using YAML, it takes a little while to figure out the syntax, the structure, the schema of these objects, and I'll show you where you can go to look up the various schemas. Okay, but all objects, regardless of whether it's a pod or service or a custom object, have these things in common. Okay, everything has to define an API version and a kind. And so this is saying, well, what is it that I'm even creating, and what API version is it associated with? And then all objects have metadata. The first item of metadata is the name, and this is going to be the name of the object. So in the case of the pod that I just created, that would be hello world. The namespace isn't always defined in the YAML document, but it can be. Otherwise, it just defaults to whatever namespace the CLI is configured to talk to. And again, we'll talk about namespaces in a future lecture, but by default, it's just going to use your current namespace. Labels and annotations, we'll again talk a little bit more about next week, but labels and annotations allow us to attach additional metadata to the objects that we create. And there's differences for when you would use labels versus annotations. And again, we'll start that discussion next week, and then revisit it quite a few times throughout the semester. Okay. So here's an example of a really simple pod definition, and it actually reflects the one that we were just building here. So I have an API version of V1. Okay, the kind is a pod. I'm going to define a pod. I'm going to specify the metadata, and the name for this pod is going to be hello world. And then the rest of this is really specific to the type of thing I'm creating. And again, I'll show you the documentation here in just a second. For a pod, I have to define a spec, which is just short for specification. And the containers that I want in this pod, I have a list. So this dash means a list. So I've got one container. This first container is going to be named hello world. And the image that it's going to use is Mixer87 hello world. Okay, so not too complicated. This is actually like a super simple pod, and they can get really, really complicated. But there's your first YAML pod definition. Now, when it comes to what goes in it, it does take time to learn, and it will take time to memorize if you ever get to the point of memorizing it. And but the Kubernetes API reference is really good, and I recommend you getting familiar with using it, especially if you decide to pursue the certification, because you can actually reference the API reference docs during the exam. And just as a quick, we'll just go to it really quickly. So on the left has several of the common application or common object types that we'll be using. But if I click on pod v1 core, it'll tell me that the group is core and the version is 1. In the the YAML document, the kind is a combination of core and, of group and version. But when it's core, you can just leave it out. It's just it defaults to the core. Anyways, we'll see more examples of other API versions in the future. But so that's where I can get my API version and the kind. And then from there, I see that every pod needs to have an API version, a kind, metadata, a spec, and a status. Now, status, just a note, it's populated by the system and it's read-only. So that's what gives us information about where it got scheduled, or is it running or not, or is it failing health checks, all that kind of stuff. But if I look at spec, I can click on pod spec, and then that will tell me what I can do from there. So my example that I had just a minute ago, I had a list of containers, and this says a container array. And if I go to the container array, okay, I can define an arg and command and environment from an image, and there's just a ton of different stuff that I can define for every single container. But also up at the spec level, I can define a lot of other stuff like the DNS config or ephemeral containers or host aliases. There's just a lot of stuff. Node selectors, and I can do affinities, and anyways, we'll talk a lot more about the other aspects of this pod spec as we go throughout this semester. So don't feel overwhelmed by it, but it would be good to get familiar with the API reference and get to know how to use it. Okay. All right. Applying the files. Once I've created my YAML file, I can use the kubectl, and we can apply it in one or two ways. Either I can give it a specific file and say kubectl apply -f pod YAML, or I can just say // which means this directory, and it'll pick up all the YAML files within the current directory. So if the pod YAML is in the current directory, then cool, it'll pick it up. And then deleting, I can do the exact same. I can use kubectl delete -f and specify the file or the directory, and it'll go from there. So let's just give that a quick try here. And I'm going to create my pod YAML, API version of v1, kind is a pod, metadata, name, hello world, and I've got my spec. And yes, I've done this a couple times, so I can rattle it off pretty quickly here. All right, that's good enough. Yep. So one of the things that you'll probably see me do is I've created an alias on my machine so that K runs kubectl, because I just don't feel like writing it out all the time. So you may see, and it's just muscle memory at this point. So you may see me do this, K apply -f, but just know that K is kubectl. It's just an alias that I've made. Okay. All right. So I'm going to apply this. I see that it's been created and the container's still creating. It'll just take a second to start up, and now it's running. All right. And I can do the same thing to delete. This time I'll just do it with the directory. And all right, there we go. Now, I'm actually going to go ahead and put it back just to set up for the last piece I want to talk about here. And this is accessing your pod via port forwarding. Port forwarding is a useful tool, and what it does is it creates a tunnel from your machine to the pod, and it does it on a very port specific basis. So I can say, hey, I want to connect, and we'll just look at the example here, port forward hello world. I want port 8080 of my machine, whenever I talk to it, to send the request to port 80 of the pod named hello world. And so this allows me to access websites or databases or whatever it is that's behind that port. And it's super useful for debugging applications. For example, I may be running a Java app and I have a Java debugger that's in the container, but I don't want to expose it to the world. I can use port forwarding to access it in a secured way. And as another note too, we'll talk about the right way to expose applications using services next week. But until then, because services bring a lot of networking, all that kind of stuff, we'll just start off with this. So let's go back to my terminal here, and I'm going to do a kubectl port forward hello world, and I want port 8080 of my machine to go to port 80 of the container. And now if I go over to Chrome, and open up localhost 8080, I'll see that first image there. So, hooray. And if I go back to my terminal now, and if I kill that just with the command C and refresh, then it'll tell me that the site's not there anymore. So that tunnel has been killed, and it's no longer there anymore. So there you are. Now, to wrap things up a little bit, this week, the hands-on is going to be just really getting your cluster up and running. We're going to go through a few basic applications and commands, and just get you familiar with doing exactly what I did of deploying a pod, describing it, deleting it, maybe even an edit, we'll see. And we'll just kind of play around a little bit. And so again, most of this week is just getting up and running, and then we're going to start picking up and using services and all that kind of stuff starting next week too. So again, this is an introduction to the container orchestration in Kubernetes. I know there's a lot of material that's packed into this almost just over 30-minute video here. But hang in there. If you feel lost, don't worry. Again, it was a lot of exposure to a lot of new stuff here. So hang in there, and we'll make it through together. And as always, if you've got questions, feel free to reach out, and I'll be happy to answer them. And until next time, I'll see you later.